All right, welcome everybody. Today we are very happy to have Robert Dougherty-Bliss from Rutgers University talk to us about union busting with stop strings.
Okay, thank you, Eric, for the introduction, and thanks, Sandra, and all the other organizers for inviting me here today. How do I sound, by the way? Is the volume okay? Am I too quiet? Am I too loud?
Sounds good to me.
Things are good? Okay. So yeah, today we're going to talk about something that I've taken to calling stop strings, which I assume that other people know about before, and it sounds like Peter's comments maybe people, but I invented a new name for them because I hadn't seen them anywhere. And the motivation for this is sort of a long story, but there's a better version here. I don't know how American the audience is or how versed in like American folklore you are. So there's this old story, old American folk legend named John Henry. So John Henry was alive back in the days of constructing the railroads. He was a steel driving man. His job was to take a steel drill and punch it mountain so they could lay down tracks and set dynamite and things like that. And the reason that John Henry is such a figure in American history, this was around the time that we were constructing things, the steam engine. So John Henry Moss, his captain, as they used to be called, came in and said, John, try and replace you. We're going to bring in something, new kind of machine, a steam engine. It's going to do your job and going to do the job of you and your brother and your cousin and your 3 friends. It's going to do the job of 6 John Henrys. And so John Henry, being quite a proud working man, decided that he wasn't going to put up with this. And he said, well, you put me to the test next to the steam engine. So they set John Henry on one part of the mountain, the steam engine right next to it, and they said, go, who can get the most done? So John Henry starts driving through the mountain, and the steam engine starts driving through the mountain. And the legend goes that John was able to drive 50 feet through the mountain, but the steam engine could drive 9 feet. But in the end, John Henry worked so hard that he dies. So there's a moral in there somewhere about automation and trying to fight the pursuit of speed and technology. I'm not quite sure what it is, but it's set up for a talk. So imagine now we're not in the days of the railroad. We're now here in 2021. Now we have factories. And in a factory, the same kind of impetus is there to automate work. So a manager decides that he's going to purchase a new experiment machine to try and replace some of his workers. Now, the union workers aren't keen on being laid off, of course. They'd like to keep their job and keep getting paid. So they decide to go on strike. They picket, they refuse to work with the machine, and they eventually strike up a deal with the boss. Now, remember the legend of old John Henry, so they don't want to have to work themselves to death to prove that they're better than them. So they decide instead they're going to subject the machine to a testing process. So every day, a union worker will walk up to the machine and inspect its work. And if the work went well, the machine goes for that day. And if the work went poorly, the machine fails for that day. So eventually, after enough days go by, the boss will get a report that looks something like this, strings of colored circles. If the machine passed, it's a green circle. If the machine failed, it's a red circle. So here are 3 possible testing regimens that might happen. And the first one, the machine fails the first 2 tests, and then passes the next 2 days, and then fails the last day. Fail the first day, pass 3 days, fail the last day, and then the last example is fail, pass, fail, pass. Fail. So this is the setup. This is what these want to try and do with this machine. Now, they know that they can't fight the machine forever. They eventually have to strike up some deal for when the testing process might stop. The boss and the workers agree to the following method of determining when to stop testing the machine and to let it back to work. So the tests will stop as soon as the machine passes half of all possible tests that's been administered consecutively. So put that a little more precisely, you'll stop at test T. Every test from T over 2 to T was a pass, not including T over 2. And here are examples of how this works. So if the machine passes the first test, that's it, you're done, you quit. No more testing. If the machine fails the first test and passes the second test, you've passed consecutively half of all possible tests. So you stop immediately, you're done in 2. If you wanted to take 4 tests, you would first 2 tests and then pass the next 2. So that, again, you pass consecutively all possible tests. And there's no other way to pass in 4 tests, because if either of these first 2 fails were a pass, you would have stopped sooner. So this is the only way to take exactly 4 tests. Similarly, for 6, you fail the first 3, pass the next 3. And things a little more interesting for 8. There are 2 possible ways to pass in exactly 8 tests. You can fail the first 4 and then pass the next 4, or you can pass 1, fail, and then pass 4 in a row. And these are the only ways. And then if you broaden the test a little bit more, there are 3 different ways to pass in exactly 10 tests. So you can fail 5 in a row, then pass 5 in a row, or the other 2 things that you see. And these are possible ways to pass in exactly 10 tests. You will note from looking at this table that there's only one odd number here, which is 1. And that is not such a surprising fact. If you sit down and think about it for a second, if you were to stop at some odd test, then you actually would have stopped at the even one right before it. So there's no way that you'll ever stop at an odd test except for the first one. So that's why you only see even numbers here. But looking at this table, I think, inspires some immediate questions. So the first question would be, how many possible testing scenarios or regimens last exactly n tests? So in other words, if you look over here, there are 3 tests that last exactly 10 steps, 2 that last exactly 8. Is there some formula that will take you from the right-hand side to the number of things on the left-hand side? And then also ask some probability questions, such as how likely is the machine to finish testing before a certain point? Or maybe the union would be interested in knowing if we can test this machine forever, actually delay the process. So how likely is the machine to ever finish testing? Test it forever. Maybe we can keep it at bay for the rest of our lives. So these are the sorts of questions we want to ask and answer here in the next 30 minutes or so. Now we're going to stop talking about colored circles because it's pretty obvious that you could translate these colored circles into binary strings, right? You can say a pass is a 0 and a fail is a 1, kind of standard like C programming analogy, I suppose. Take a binary string, call the bits B1, B2, B3. It could be a finite binary string, it could be an infinite binary string, it doesn't matter. The definition is the same. And you say that you're stopped at an index t if all the bits from t over 2 to t are 0. And what we're interested in is the stopping time of these strings, which is the time that you see this long run of zeros in the back half. So the stopping time is the smallest such t that you see this, or infinity if none exists. And then here are 3 examples. So this first string, 1, 1, 0, 0, the first time it passes has a run of zeros that equals half string is at the last position, which is 4. And these other ones here, 1, 0, 1, 0, 0, 0, it stopped at time 2 and at time 6. So its stopping time is actually 2, not 6. And if you were to look at an infinite string of 1s, it has stopping time infinity. It never stops anywhere. So every question that we asked about these testing, these colored dots, can pretty obviously be reframed in terms of binary strings. So you can ask, how many binary strings of length n have stopping time n? Or what proportion of binary strings of a certain length will be stopped at that point, or something like that. We can reformulate these all in terms of binary strings. So this is actually what we're going to talk about for the next 30 minutes or so, these binary strings rather than this machine testing process. So now's probably a good time to ask, is everyone good so far? Has anyone tripped up on any of the definitions? Any questions? Okay, good. Maybe that was an insulting question. I don't know. Let's see. So let's start off with the enumeration process, since we're here at the New York Combinatorics seminar. Let's start off with actually doing a little bit of combinatorics. So we want to try and find a way to count how many strings there are that's at a certain time. Here's a sequence for us. This sequence is the number of binary strings of length n with stop time n. Looking back at the table we saw earlier, this is the number of times that a given number appears on the right-hand side. So the sequence starts off 1, 1, 0, 1, 0, 1, 0, 2, 0, 3. And looking at it, we're seeing some zeros in the odd positions, which is interesting, except for this leading 1. But this is actually an obvious fact that it's going to be 0 there, just from what I said earlier, that no string have an odd stopping time except for 1. So let's ignore that leading 1 for now, set it aside as a special case, and just look at the even term, because we know all the other odd terms are 0. So the sequence that we're looking at initially is 1, 1, 2, 3, which is not a lot of information. So if you look this up in the OEIS, there's about 26 different sequences that it could. So obviously, this is not good enough. We need a little more data. And we have a little bit more data here. So you can write a program to enumerate all these strings. Strictly speaking, enumerating all binary strings is an exponential time algorithm, but you can crank out enough data here. Maybe you can go like n equals 20 or something before your computer starts. So if you have more terms, you get down to 40 sequences. A few more terms, you get down to 4 sequences. You get just enough terms, you'll see that there's only one sequence in the OEIS that matches these numbers. And if you look at these numbers, before I give it away, it is not obvious to me that there's a pattern here. Sometimes it looks like you're doubling. Like if you go from 3 to 6, you're doubling. From 11 to 22, you're doubling. But other times you're not doubling. So there's something else going on. But fortunately, Neil Sloan's OEIS saves the day. And it turns out our sequence looks like A2083. And these are the Narayana-Zidek-Capell numbers, or maybe Capell numbers. This is a sequence of numbers defined by this recurrence here. So it starts off 1, 1. Then after that, to get the next even index term, you double the previous odd term. And to get the next odd index term, you double the previous term and subtract off some earlier term in the sequence. And this was a pretty surprising discovery. It was exciting because action is not mentioned in the OEIS. Narayana, and Capell invented these to study different things that we're going to talk about in a second. But for such a small a number, the 2000s, it's always exciting to find a new connection you haven't seen before, because surely someone would have thought of this, you would think. Say like, A50 seems like we've probably everything it could possibly enumerate by now. So this was exciting. But to try and get at this conjecture, of course, it's useful to know what these things actually enumerate. I'll call these the Narayana numbers from now on, because that's a little bit easier to say than Narayana-Zidek-Capell. So Narayana and Capell wrote this paper back in the 70s, where they're trying to enumerate what they called random knockout tournaments. And I think that's a terrible name for them. Apologies to Narayana-Capell. I'm going to call them instead multi-round knockout tournaments, because I think that makes a little more sense for what we're trying to count here. And it's best explained through a picture. So I'm not sure how many fans of March Madness are here, college basketball fans. What they're trying to enumerate is all the possible ways that you could structure a knockout tournament between a certain number of players. So if you look at March Madness, you have 64 teams that's cut down to 32 teams and so on. So that's one possible structure to play that tournament, but you could have did it in different ways. So here's an example tournament where you have 6 players that need to play. So you have 6 players, 2 players go head to head, the winner moves on, the loser is eliminated, and you need to somehow trim them down to a single champion. And here's one possible structure where you have 6 players. You start off in the first round with 2 games. So there are 4 players in the first round, and 2 of the players sit out. There's 2 have a bye. They don't play the first round. Then in the next round, you have 2 more games where the players who have a bye now join into the fray, and they compete against the winners of the first round. And then whoever wins that goes into the final round, and whoever wins the final round. So we would represent this, or Narayana and Capell would represent this as 2-2-1. There are 2 games in the first round, 2 games in the second round, and 1 game in the final round. And T of n is the number of configurations of these tournaments. Okay, is this picture clear, sort of what we're trying to enumerate here, at least graphically? Okay, excellent. And to explain this a little more formally, what these numbers are creating is a list. So you have a list describing here. For example, the list was 221. So I have a list of numbers where number represents how many games are being played in a certain round. So there are M1 games in the first round, M2 games in the second round, and so on, MR games in the final round. And the conditions that these are subject to are, first of all, you have to only crown 1 from the tournament. So every game eliminates 1 player, which means that the sum of the number of games needs to be 1 less than the number of players that you have. So you trim the field down to 1 champion. The next condition these are subject to is can't have too many games for the number of players that you have, because every game will eliminate some number of players. And so I couldn't say I need, I'm going to have, say, 10 games and I only have 19 players, for example, or something like that. I wouldn't have enough players. So every game requires 2 players. And this expression here on the right side, this is how many players would be left at the I. So that's just a compatibility condition there. And then finally, you're trying to crown a champion. So the last round can only have 1 game between 2 different players. So T of n is the number of lists, these M's that satisfy these conditions. And if you look at it for a second, you'll realize these are actually like restricted compositions of n minus 1. So you have the compositions of n minus 1, and then you throw this inequality restriction on them, make sure the last one is 1. And that's what Narayana and Capell were rating back in the 70s. Now, it turns out our conjecture is true. The binary string length 2n with stop time 2n exactly equals the nth Narayana number. And we have some explicit bijections. I'll give you an example of how bijection works. Start our example of 2-2. So this is a knockout tournament. It's the one that we saw earlier. 2-2-1 is a knockout tournament on 6 players. So our theorem tells us we should expect a binary string of length 12 with stopping time 12 out of our bijection. Here's how it works. You take 2-2-1, you append a 1 to it, then you reverse the string. 2-2-1 becomes 2-2-1, and then you flip it to get 1-1-2-2. Then the more complicated step is you take every index there, every bit, or not bit, every value, and if the equals x, you replace it with x minus 1 zeros, and then a single 1. This first 1 gets sent to 1 because 1 minus 1 is 0, so you don't introduce any other zeros. 1 gets sent to 1, and 2 gets sent to 0, 1, and 2 again gets sent to 0, 1. And this is a string of length 6, which is not stopped. It has stopping time infinity, if you want to think of it that way. So the next step then is to just throw 6 zeros at the end to make sure that it is. So now this is a string of length 12 with stopping time 12. It's stopped at 12, and it's not stopped anytime earlier than 12. And this is pretty clearly an injection, I think. Every step that we did is reversible. Appending a 1 and reversing this, you can clearly reverse that. There's an algorithm to go from this step backwards, and this is just throwing some stuff at the end there. The only question is it surjective, and it's not so hard if you sit down and think about it to see that it is surjective. So we have a nice bijection taking from the knockout tournaments over to the stop strings that we were trying to enumerate, which is a pretty neat answer, something that is not yet mentioned in the OEIS, but we should probably be in there at some point. We're working on it, I promise. The next questions that we asked were ones about proportions, which was what proportion of binary strings stopped at a certain time, and things like that. These were the 2 questions exactly, actually. How many strings of length 2n have stopping time 2n, and then how many binary strings of length 2n have stopping time less than or equal to 2n. How many strings are stopped by a time, maybe not at a certain time. And now that we have our enumeration theorem related our strings to the Narayana numbers, we have exact answers to these actually. So the first one, how many binary strings are there? I guess say how many here, I mean what portion really. How many binary strings are there of length 2n with stopping time 2n? Our theorem says that it's the nth Narayana number. And then how many binary strings are there? Well, 2 to the 2. Good. This is a simple thing. The second question is a little more complicated. Let me try and explain where this expression comes from. If you take a binary string that's stopped at some time 4, 2 to the n, all of those possible strings are enumerated by the Narayana numbers, and then you can put whatever you want in the string that stops. It's some arbitrary bits, it doesn't matter. So that's how you end up getting this sort of convolution of Narayana numbers and 2 to n. But the takeaway, the real highlight here is that this simplifies. The exact proportion is this expression right here, a partial sum of the Narayana numbers divided by powers of 4. So actually, partial sums of this guy, I suppose. These are exact answers to these questions, but obviously we aren't really satisfied with this. We want a little more qualitative what's going on here. So this clearly reduces to looking at properties of Narayana numbers. What are the asymptotic properties? What are they, are they bounded by something? And do they grow exponentially? What do they look like? So the first step to think about sequences is usually plot them and see what they look like. So here's a sequence of Narayana numbers plot, a logarithmic plot. This is a log 2 plot. And because we have this really nice straight line, I guess the first obvious guess would be that the Narayana numbers are probably on the order of 2 to the n. But because this is almost an exactly straight line, slope 1, we might even guess that the Narayana numbers are equal to a constant times 2 to the n, at least asymptotically. And to get at that, we need to go back to the recurrence that defined them. So this was the recurrence. There's some initial condition that matter so much. The recurrence was this almost doubling process. And if you go down and work through some of the details and think about it, it turns out that the sequence t of n divided by 2 to the n, this is monotonically decreasing. And that means that the Narayana numbers are definitely on the order of 2 to the n, but it's still possible that they're a lot smaller than 2 to the n. This quotient converges to 0. So the question is, does it converge to 0 or positive constant? Are the Narayana numbers a lot smaller than 2 to the n, or are they actually 2 to the n? And for us, thankfully, Narayana and Capell prove that they are actually roughly equal to 2 to the n. They're some constant times 2 to the n, and the constant happens to be about 0.0792 or whatever. So this proof is not super difficult to go through. They sort of prove it as an afterthought in their paper back in the 70s, but it's still useful because it gives us some really nice answers to our questions. So the first one was, what proportion of strings of length 2n have stopping time 2n? And the answer is almost none of them. So you can replace the Narayana number with c times 2 to the n. Look at this, the proportion is vanishingly small. It's not just 0, it's almost 0. So hardly any strings will have a fixed stopping time pick. If how many strings have stopping time 6 or stopping time 100, 100, almost none of them, basically. But in an interesting note, the second question has a very big answer comparison. So the number of strings of length 2n that have stopped by 2n is roughly 84% of all possible strings. And that's because t of k, the kth Narayana number, is roughly 2 to the k. So this series converges really quick, which gives us a nice estimate of this guy right here. It's pretty easy, just keep like the first 1,000 terms and you get this almost very stable convergence here. So if we interpret this back in the union context, this says that if you test the machine for long enough, there's an 84% chance that it will eventually finish testing, which is not great. That means the union only has a 15% chance to beat against big corporations and to win for workers' rights or something. Not a good gamble. I wouldn't make that bet. But this second answer here is a little strange, I think, because I'm trying to interpret this as a probability, saying like the probability that if you test forever, you'll finish at some point is 84%. It's not immediately obvious to me how to actually interpret this limit in a probabilistic context. Maybe someone a little better at probability than me can do that. But this is like a nice heuristic argument for, I think, if you test forever, roughly 84% of things should eventually stop. Fortunately, it turns out that you can actually do the same thing in a little more rigorous of a probabilistic context. We just have to borrow a little bit of measure theory. So a more natural way to think about probabilities on infinite binary strings is to translate back to the real number. So every real in 0, 1 has a binary expansion, which tells us that you can basically identify all binary sequences with reals in the unit interval and vice versa. So this is how we're going to get probabilities in a little bit different way here. So take the reals in 0, 1, and I always mean closed 0, 1. I wrote over 1 here, but it doesn't matter so much, but I meant closed 0, 1. Let Sk be a subset of the unit interval. It's all the reals that when you think of them as an infinite binary sequence, they have stop time k. And what we're really interested in here is what is the Lebesgue measure of the union of the Sk. So this, in some sense, ought to tell us actually the probability that at some point we would stop. So this union here, this represents all the strings that have some finite stopping time, and the measure of this should tell us what proportion of strings at some point. This is what we want to know. And fortunately, this is actually a discrete union because you can't have time, 7, or well, you can't have stopping time at all. You can't have stopping time, say 10 and 20. The stopping time is sort of a unique function. So we just need to know the measure of each of the sets Sk individually. And here's a nifty to get a better sense for what this thing looks like. So this is an approximation of a plot, actually. Let me explain what I'm trying to do here. So you look at the unit interval, 0, 1, and pick a real number. Then you write its binary expansion, and you compute its stop time. Then you plot that stopping time of real, and that graph is. This first horizontal strip, 0 to half in the middle of the screen, these are all the reals that have stopping time 1. And those are the reals that start off with 0.0 in binary. Because if you thought of, a binary string that starts with a 0 immediately finishes the testing process. You stop. All of these reals will have stop time 1. Then the second horizontal strip is at height 2, and it's all the reals that have stopping time 2. These are the reals that start off with 0.0 or 0.10. That's where they start. And this actually goes from a half to 3/4. Say that again in a second. But you'll see as you get closer and closer to 1, this graph starts to get more and more unusual. And actually, you really shouldn't know what the graph looks like up here at this point because the dots are too close together to really see where the gap should be. So you'll see the dots, these big gaps here, but eventually they get closer and closer. And it's not really, you can only make the dots so small before you can't read them on a slide. So this is a rough approximation. Some other misleading things about this plot is that this is necessarily only an approximation of the real plot because stopping times can be as big as you want. The plot is actually unbounded, it goes off to infinity. But when you're dealing random points in the real line, you can only ever sample, a random approximation to a point. You can only sample finitely many digits, basically, binary digits. So this is not what the real plot looks like. And lastly, this function is not well defined on every point of the real line. If you want real values, you could define it to be infinity. But if you take a string that has stopping time infinity, then what do you plot? Function. So the question we're really asking is, what is the portion of the unit interval where this function is well defined, where there is some stopping time? And I think sort of naively, if you just look at this, it's not hard to tell, but it sure looks like it's defined everywhere. I mean, you need to zoom in really far to see where the gaps might be here. Is there a tiny gap between some of these dots where it's not defined? It's hard to tell, but that's sort of what we're really asking here is, when can we define this function? Okay, very pretty plot. I like this plot. Now let's get a feel for what these sets SK actually look like, though. So I mentioned this earlier, but let's go through it again. So what is the set S1? It's a subset of the unit interval. It's all the reals that, when you think of them as a binary string, have stopping time 1. There's only one way to have stopping time 1, and that's you start with a 0. You start with a 0, immediately you're stopped, you're done, no more questions. And as soon as you change that 0 to a 1, you have stop time greater than 1. So the first bit in the binary expansion needs to be 0, but then everything else is totally arbitrary. You can do whatever you want. So you're good as long as you stay from 0.0 to 0.1 in the binary expansion, and you don't include 0.1, which works out to be, of course, 0 to a half. And that means this first horizontal strip right there, 0 to a half. The next horizontal strip works very similarly. So the set S2 is a set of all the reals with stopping time 2. So the only way to have stopping time 2 is for you to fail your first and then pass your second test. So you have to start with a 1, 0. And then as soon as that second 0 becomes a 1, you have a later stopping time. So S2 is the set of all the reals from 0.10 to 0.11 in the expansion, which is a half to 3/4. And that extends this strip right here, going from a half to 3/4. So that 3/4 of the unit interval are and well defined. What happens later that gets more interesting. In general, the description works exactly the same way. So SK is actually a union of intervals of a certain length. So what you do is you look at all of the strings that have length K and stopping time K. For example, here, the strings of length 1 with stopping time 1 was just 0. The strings of length 2 with stopping time 2 was 1, 0. That's it. And then you form a little interval that basically says, okay, as long as your first K bits are this, you're stopped. And as soon as you change your last bit, you're going to see something different. You'll have a different time. It'll be higher than what it was. So you take the union of all of these intervals and have length 2 to the K. And the adding 1 over 2 to the K just means you flip the last bit from a 0 to a 1. That's all that means. The nice thing about this union is this is actually a disjoint union. So if you take in 2 distinct binary strings of length K and you flip the last bit, you're not going to see any overlap here. These different disjoint intervals on the real line. And that's great because we know the measure of this interval then. It's just its length, which is 1 over 2 to the K. So the measure of SK is actually just the number of binary strings of length K with stopping time K divided by 2 to the K. And that's a lot of words to say, but if you sort of trace the details, it turns out the measure of the full union is this expression right here. It's exactly the same answer that we got before. So our weird heuristic actually turned out to be right. And the real proportion of binary strings that stop at some point is about 4%. And I assume, I don't know for sure, that what we did before is actually proof of this fact. You can probably think of some set that grows up our set and then use the monotone convergence theorem or something. It probably is a proof, but I feel a lot better at this fact in our belts. Okay. Any questions before we go on about the measures of this or anything else? No, perfect, excellent. All right, let's recap what we've said so far, because now we've answered all of our main questions in a few different ways, actually. So our 3 main questions were, how many testing regimens are there that last exactly in tests? And we answered that. It's, the Narayana numbers are roughly exponential. They're 2 to the n. So there we go. We know the answer. Although for this to be correct, maybe this should be a 2n rather than an n. But the Narayana numbers are the answer to the first question, and we know what they do asymptotically. So that's a definite answer. And then the next 2 questions we had were, how likely is the machine to the testing in a certain point, and how likely is it to ever finish testing? And the second question had sort of an unsatisfying exact answer, but we know that it converges to the answer to the third, which is probability, it turns out. It's around 84% of the time you will stop testing. So this is it. This is a definite answer to our question. So great, we've kind of wrapped everything up. What's left over to do is how can you change this problem a little bit? Because in some sense, it seems like things work out a bit too neatly to not generalize. It's not at all obvious why binary strings are important. Maybe they're not important. What if you did this in base 3 or 4 or base 5 or whatever? You can go through the same arguments and maybe try and do the same thing. You almost definitely won't get the Narayana number, but maybe you'll get something else. The other way that you could generalize this is, rather than think about the interval t over 2 to t, why don't you think about a different interval? Rather than looking at the back half of a string, why don't you look at, say, the back third of a string, the back 3/4 of a string, or something more exotic than that? Lots of different things that you could do there that would change this problem and give you different answers. So I want to talk about both of these a little bit, and we're going to go in reverse order from what's on the slide, and we're going to do the base generalization first, then talk about the intervals. So the definition in both of these cases, you need to restate it just to make sure we all know what we're talking about. The definition is actually exactly the same as it was for stop strings, except now the bits are allowed to be something else. So we're working in base B now. So we say the bits are not bits anymore. The digits are D1, D2, D3, up to whatever. So now they can be more than 0 and 1. They can be 0, 1, 2, 3, whatever, up to your base, -1. But the definition of stop is still the same. You're looking for a long run of zeros, not a long run of something else. So you want to know when you see a run of zeros that takes up the back half of your string. And the stopping time is still exactly the same as it was. It turns out that there is still a nice enumeration theorem here. In fact, it's exactly the same answer. So the number of B array strings of length 2n with stopping time 2n equals new sequence T sub B of n, which satisfies this recurrence. And the important part is that this is the same recurrence that the Narayana numbers satisfy. Only the initial conditions are different. If you took B to be 2, you're working binary sequences. Then the initial conditions are 1, 1, then satisfy the Narayana recurrence, which means that you are the Narayana numbers. So B2 recovers everything that we just said in the past 40 minutes. But for B greater than 2, these sequences are not in the OEIS. So we should probably put them there. We will at some point. I think it's maybe an interesting question to ask, are there also generations of the knockout tournaments that Narayana and Capell were thinking about to higher bases? We don't know, we're not sure, but that could be in there, and that's worth thinking about. And also mentioning in the OEIS if it's true. But for the time being, we definitely have these recurrences. This is a nice enumerated term that we have. And these sequences satisfy very similar properties. So the Narayana numbers are roughly a constant times 2 to the n. It turns out that our base B sequences, the enumeration sequences, are also some constant times B to the n. This sort of directly generalizes the Narayana result. We even have a nice bound on what the constants could be. How we found this proof is nifty. We actually sat down and we wrote a program that for any fixed B will automatically find a proof of this fact. But the program only worked for fixed numeric B. You could plug in B equals 7 or B equals 8 or whatever, and it would say, okay, here's a proof for you. And then we had to go back and sort of tinker with what it was saying and try and generalize it to arbitrary B. But you end up getting this bound if you do that. And so the constants go something like this. This is exactly the constant we saw back in the theorem of Narayana and Capell. And then these are some new constants that seem sort of arbitrary and random. But there they are. And the sort of interesting thing about this is if you go through the same process with binary expansion we did for the unit interval, so identify every real with its binary expansion, well, you can do the same thing with different base expansions. So let SB be the set of reals in the unit interval which have a stopped B area expansion. Exactly the same thing we did before. And we can go through and find the measure of this set in exactly the same way that we did before. And it turns out the measure is something like 2 over B asymptotically. So this first number here, this is exactly the measure that we saw before when we were talking about the binary case. And then these measures get smaller and smaller and smaller. And they should be roughly equal to 2 over B. So if you look at B equals 6, this is 0.3 something, and we expect it to be a third. So that's a pretty good approximation, all things considered. And these sets get smaller and smaller and smaller. So you blot out different parts of the real line, and eventually your blots get smaller, and they will decrease down to approximately a set of measure 0, but they'll always have some positive measure, never get to be exactly measure 0. These constants here, the measures and the C's, the asymptotics, seem totally arbitrary. I don't expect there to be any nice properties that we could prove about these, although just because I'm here and this is a talk, I'm sure they're all irrational. So, good luck trying to prove that. But it seems unlikely that we could ever say anything about it, but it'd be really surprising if we could. Now, the next way that you can generalize these is, instead of sort of toying with the base that you're expecting all of your numbers, your sequences in, you can toy around with the interval. So let's go back to binary for now, just because it's what we were talking about. It's easier to think about. So take a binary sequence, and now we're going to introduce a function definition. Just pick some arbitrary function f, it doesn't matter what it is, just some function that takes in integers. I'm going to say that you are f stopped, f is the function, at an index t, if all the bits between t minus ft and t are 0. And we'll call these f stop, they have f stopping times and whatever else you want to talk about. And so now the question is, what happens if you take different f's to the stopping points? What do the enumeration sequences look like? What do the subsets of the interval look like? What are their measures? This is sort of the next interesting question. And to give you a feel for the intuition, taking a bigger function means that the interval will be bigger, which means that you're less likely to be stopped. It's harder to stop. And like any good generalization, obviously we can recover everything we said before using. So if you took f of n to be n over 2, that's exactly what we were doing in the beginning. Those are binary stop strings with no qualifiers. And experimentally, though we haven't actually worked out the details here, if you let f of n be some rational multiple of n, then it looks like very similar stuff happens. You're going to get a recurrence that is something like the n over 2 case, and you're going to get measures that are something like the n over 2 case, but maybe not exactly the same. It's still something to explore, but it's worth thinking about. But the more exciting thing is kind of having a more exotic function. So the most interesting thing that you could give, or the least interesting thing, I guess, is your function can't be any bigger than linear. If it were like n squared or something, then eventually the interval is actually the entire string. So that's not going to work. So it has to be less than n, or less than some multiple n in some way. Means that if you want to look at interesting stuff, you have to go below the linear case. And the next step is to say, well, what if f of t were like log t or something like that? And we have an exciting theorem that we just proved yesterday, actually. So almost every real in the unit interval is log stopped. So if you look at the interval, take the unit interval to spell this out. If you take a real and write down its binary expansion, then there will be some index t such that the bits t minus log t through t are all 0. This is something that we proved. This is an interesting thing because it shows that there's some crossover point where before in the previous, when we had f of n equals n over 2, not every real was stopped. There was some way that you could squeak through the testing process and carry on. You would never finish. But this says that if you're testing a small enough interval on the log order, and it turns out you cannot ever squeak through. At some point, you will hit zero, almost surely anyway. And what we think maybe happens, although we don't know because this is still hot off the presses, perhaps there's a threshold function where if your interval is big enough, then you don't ever stop. You don't stop everywhere. And if your interval is small enough, then you do every stop. Maybe there's this nice threshold function theta where you would be stopped if and only if you're small compared to theta. And I don't know, maybe the theta is the logarithm. I'm not sure. This is something we're still thinking about, but it seems possible that there could be some spot where you flip from one to the other. We don't entirely know, but we hope we will have something more to say about this in the next few weeks, months. I think this is all that I have to say for the talk. I do want to wrap up saying that I think it's unlikely that other people have not thought about this before. In some, even Peter, before the talk, mentioned that things similar to this have been thought about in different contexts. And I would wager that almost definitely a statistician somewhere has thought about a problem that looks something like this. You know, you have a test, and the question is, how likely is it that you'll see a test result, a consecutive number? Surely that's some statistical question somewhere, maybe, that someone's thought about in a different context. And so it would be really nice to know if we are thinking about something that someone else already has cool things to say and how maybe contribute there. But for now, this is all we have to contribute to the problem. So thanks everyone for listening, but I will stop here.
All right, thanks Robert for a great talk. Are there questions or comments? So these Narayana numbers, the recurrence they satisfy is quite unusual in some sense.
It is, yeah.
Does that mean that they belong to some nice class of sequences that satisfy similar recurrences? Or are they holonomic, for example?
They do actually, I'm having to scroll back, here we go, the recurrence. So they do actually belong to a family of sequences that is not very nice. They're not holonomic, I don't think, because they satisfy some weird, parity condition for the recurrence. But it turns out, if you go look at the OEIS entry, it mentions this, the nth Narayana number is actually, so T of n equals the sum from k equals 1 to floor of n over 2 of T of k. So the Narayana number is the sum of the previous half numbers or something like that. I forget what that condition is. So it turns out this means that they are something called a meta-Fibonacci sequence. They are a sum of some previous terms of the sequence. And people have thought about this before, but it's not a very well understood subject, I don't think.
Yeah, and in the middle of those three equations, the coefficient 2, you immediately think, oh, well, it's because we're working on a binary alphabet. But when you showed the recurrence for T sub B, the generalization, that 2 is still there. So that's not what's going on, I guess.
Exactly, right. That is, yeah, it is sort of, let's see, the generalization, it was somewhere around here. Here we are, yeah. I was also surprised. The generalization, it turns out, only requires a 2. There's no, the base only appears in the initial conditions, which obviously dictates the behavior, but not in the same way that you would expect. I also thought maybe there should be a B here and maybe a B one there. But no, it turns out.
It's really interesting.
Good questions or comments.
Are there any other questions? All right, well, let's thank Robert again for a great talk.